In the next topic, I'm going to show you how to calculate the limits of function into variables. So the first thing I want to show you here is limits of constant and linear functions. Let a, b, and c be real numbers. For constant function of the form f of x, y equal to c, the limit of the constant function as x and y approaches the point a, b is going to be equal to the constant itself. For linear function of the form f of x, y equal to x, the limit of x as x, y approaches the point a, b is equal to a. And for the last function, the linear function of the form f of x, y equal to y, the limit of the function y as x, y approaches the point a, b is equal to b. As you can see here, for this constant function, there's no xy dependence, so therefore the limit of the constant c is itself. For the limit of linear function of the form x, as x, y approaches a, b, as you can see, this function does not have y, so by direct substitutions that you see in single variable calculus, you can directly apply to this case. Therefore, the limit of the function is equal to a. Similarly, in the case of limit of the linear function y, as xy approaches the point a, b, by direct substitution, you let y equal to b, and therefore the limit is equal to b. So we can make this calculation under the assumptions that the functions of considerations are continuous functions, and it's true in the case of constant function and linear functions or polynomial functions. Some of the limit laws that you see in single variable calculus again can be directly applied to functions of two variables. So let's take a look at the following limit laws. So let capital L and capital M be real numbers, and suppose that the limit of the function f of xy as xy approaches a, b equal to L, and the limit of the function g of xy as xy approaches a, b equal to capital M, and assume that c is a constant and n greater than 0 is an integer. So you have sum and difference law, that is, limit of the sum is equal to the sum of limit, and limit of difference is difference of limit. And because we make the assumptions that limit of f of xy as xy approaches a, b equal to L, and limit of g of xy as xy approaches a, b equal to M, therefore the limit of the sum is equal to L plus M, and the limit of the difference is L minus M. For constant multiple, you have the limit of c multiplied with f of xy as xy approaches the point a, b. Instead of calculating the limit of the scale function, what you do is you calculate the limit of the original functions and scale the resulting limits. For the product law, limit of a product is product of limits. And for quotient, is limit of a quotient is quotient of limits. And this is equal to L over M, provided that M is different from 0. That is the limit of the function g of xy as xy approaches a, b cannot be equal to 0. For power, what it says is that instead of calculating the limit of f of xy raised to the power n as xy approaches the point a, b, you can calculate the limit of the original function first and then raise the resulting value to the n power. Similarly, for the root law, instead of calculating the limit of the functions at is raised to the power 1 over n, or the root n for that matter, you can calculate the limit of the original function first, and then raise the limiting value to the power 1 over n, or take the n root of the limiting value. This law, again, very similar to the one that you see in single variable calculus. Now let's apply this law to some example. So in the first example, I want to evaluate the limit of the function 3x squared y plus square root of xy as xy approaches 2, 8. So for this first example, I'm going to work a little bit slowly, provide the laws that I use for each step of the calculations. So the limit's going to be equal to limit of 3x squared y as xy approaches 2, 8 plus limit as x, y approaches 2, 8 of square root of xy. So I use the sum law in this case. Again, the sum law is saying that the limit of the sum is the sum of limits. Now for the first limit, you see 3 is the constant multiple, so I can pull 3 out of the limit operations. I get 3 times limit as x, y approaches 2, 8 of x squared y. And for the second limit, this is the root law. So instead of calculating the limit of square root of xy, I'm just going to calculate the limit of xy and then take the square root of the limiting value later. So here this is equal to square root of limit of xy as x, y approaches the point 2, 8. So I want to know that for the first limit, I use constant multiple law. And for the second limit, I use the root law. Now to obtain the limiting value, I'm just going to use direct substitutions. So x equal to 2 and y equal to 8, and I get 3 times 2 squared times 8 plus square root of x, limit of x times y. So again, x equal to 2 and y equal to 8. So here I get 2 times 8. If you do the calculations correctly, the first term we're going to obtain 96 plus square root of 16. So this is 96 plus 4. This is equal to 100. So the limit of this function as x comma y approaches 2 comma 8 is going to be equal to 100. In the next example, I want to find the limit of the functions 2x plus 3y over 4x minus 3y as x comma y approaches 2 comma negative 1. So this is a rational function, or this is a fraction, so you don't want 0 in the denominator. The domain of this function consists of all the point x comma y in R2 such that 4x minus 3 is different from 0. So that's usually what you're going to do when you see a fractions. But a quick check also allows you to see that the point 2 comma negative 1 is actually not going to make the denominator 0 at all. In calculating this limit, I have a limit of a quotient is going to be equal to quotient of limits. So this is equal to limit of 2x plus 3y as x comma y approaches 2 comma negative 1 altogether divided by the limit as x comma y approaches 2 comma negative 1 of 4x minus 3y. Here for this step, I use quotient law. Now for the numerator, I have the limit of the sum is the sum of limit. The limit as x comma y approaches 2 comma negative 1 of 2x, then plus the limit of 3y as x comma y approaches 2 comma negative 1. And then in the denominator, you have limit as x comma y approaches 2 negative 1 of 4x minus limits as x comma y approaches 2 comma negative 1 of 3y. So on the numerator, I actually apply the sum law, and in the denominator, I apply a difference law. And then for each limit that you can see in the fractions, you apply the constant multiple. That is, you pull the constant out of the limit operations and then apply direct substitutions in order to calculate the limit. So here you have 2 times 2 plus 3 times negative 1 on the numerator, and in the denominator you get 4 times 2 minus 3 times negative 1. So you get 4 minus 3 divided by 8 plus 3. So this is going to be equal to 1 over 11. Now in example 3, I'm going to stop mentioning on the laws that I use in the calculations and just focus on getting the answer for the limit of the functions. So if you notice that the function is a fraction, the domain of the function is on the points x comma y in R2 such that the denominator is not going to be equal to 0, so that is x is different from 0 and y is different from 0, so you avoid the origin. Right, so you're going to take in all the value of x and y except the origins. So therefore, when calculating the limit of the function at x comma y approaches 2 comma 1, this is going to work. Again, if you apply the laws, you can just say that, okay, the limit of a quotient is quotient of limit, limit of the product on the numerator is going to be the product of limit, so on and so forth. But I'm just going to ignore all of that and use direct substitution in this case because I understand that I know that the function is going to be continuous at the point 2 comma 1. Right. So here, by direct substitutions, you're going to get negative 2 times 1 over negative 2 squared plus 1 squared, or this is negative 2 over 4 plus 1, or this is negative 2 over 5. So that's going to be the answer of this problem. Again, most of the time, as you understand, in single variable calculus, it's fine for us to use direct substitutions when calculating the limit of functions.